In this video, I'm going to work through numerous examples of conservation of mechanical energy. Here is our first example. We have a pendulum that is pulled back to give it 6 joules of energy and is released from rest. I want to know the energy transformations that take place as it swings. Okay. There's no spring involved in this, so we don't have to worry about elastic potential. Initial position, it's pulled back, and what we know is it's released from rest. So if we make a chart let me try one more time to get that line roughly straight. Oop, that's not what I wanted. Better. Better again. Good enough. Okay. We are told at this point it's given 6 joules of energy and it's released from rest, which means it's not moving. Therefore, it cannot have any kinetic energy, so our GPE has to be 6 joules. It then begins to swing. So the aim here is this is where it was originally, this is where it is now. Yes, it has some GPE. Yes, it has some kinetic energy. We don't have enough information to say how much of each it has, so we'll just give it 6 joules total. It then hits the equilibrium position. At the equilibrium position, it's at the bottom of its motion. Therefore, we put our 0 for gravitational potential there, which means since the total still has to be 6 joules, it has to have 6 joules of kinetic. It's moving there. It can then swing through someplace on the other side. Yes, it will have gravitational. Yes, it will have kinetic. Total still has to be 6. And finally, it swings, So in theory, this angle here and that angle there are the same, which means it's back to having 6 joules of gravitational potential energy, no kinetic, which gives it 6 joules total. For our second example, we're dealing with a horizontally oscillating mass on a spring. So I'm going to treat this one like I did the last one and draw multiple locations. Just setting them up here, guys. But look at how pretty and straight my lines are. So this is going to be our initial location, and I'm going to keep track of EPE, KE, and E total for these 3 positions. Initially, we are told it has 5 joules of energy, and the idea here is that it's either pulled out or compressed from its equilibrium position, which I'm going to let be the dotted line here, and label it with an EQ, so that it has 5 joules of elastic potential at this location because it's not moving. It has no kinetic, which makes our total 5 joules. It then is released and it starts moving. At some point in between the equilibrium position and its max position, it will have both elastic and kinetic, and whatever those two are, they still have to add up to 5 joules. At the equilibrium position, the elastic goes to 0, which means all our energy has to be kinetic. So we have 5 joules of kinetic energy and our total is still 5 joules. But it's moving, which means it pulls through the equilibrium position, and we are somewhere on the other side where it is compressed and it is still moving. We don't know what those two numbers are, but they have to total 5 joules. And finally, it is compressed maximally, which means it has stopped moving. We have 5 joules of energy, and that is all elastic potential. In the next example, we have a mass on a spring, but now it's oscillating vertically. So I'm going to do something very similar, but because we're oscillating vertically, we have to consider GPE, EPE, and KE in our considerations. And I'm going to put E total at the top because I ran out of room at the bottom. So what does it look like initially? Here's my spring. It's pulled down. There's my mass. At this location, it's pulled down as far as it is going to be. It is at rest. We are told it has 5 joules of energy, and that energy has to be all elastic potential because it's at the bottom of its motion, so there's no gravitational potential, and it is not moving. As I did on the last slide, I'm going to define the equilibrium position. Let's put it there, just as a reference. So we release it, it starts moving upward. At this point, it still has elastic potential because we are slightly stretched. It has gravitational potential because it is up above the bottom. Oh, I put my first Y in the wrong spot. Sorry about that. There we go. It has gravitational potential because it's up above the bottom. It has elastic potential because we're still stretched, and it is moving, so it will have kinetic, but whatever those are, they still have to add up to 5 joules. Next, we're going to hit the equilibrium position. Energy has to be conserved, so that has to be 5 joules. It does have gravitational potential, and kinetic because it is moving, and at this location the kinetic energy will be as big as possible. It will not have elastic potential because it is at the equilibrium position. It then squishes through. Right. Now still 5 joules, but I am slightly compressed, so that gives me some elastic potential. I'm still above the bottom, so I have gravitational potential, and I have kinetic, so I have to add all 3 of those up to get my 5 joules. And lastly, I hit the max of its motion. At the maximum position, it stops moving, so kinetic goes to 0. It is compressed, so I have elastic, and I am above the bottom, so I have gravitational potential, and it still has to total 5 joules. Next example. I have a ball dropped. At some point during its fall, it has 5 joules of potential energy and 10 joules of kinetic. Describe the energy transformations that took place. No springs, so I don't have to worry about them. I do have GPE, KE, and the total energy. Here's my ball. Here is the bottom. It's dropped from rest, which means at the top it only has gravitational potential, and it's going to fall such that at the bottom, at the ground, it's only going to have kinetic. But somewhere in the middle, we're told, at this point, it has 5 joules of gravitational potential and 10 joules of kinetic, which means it has a total energy of 15 joules. Which means at the top, where our energy is all gravitational potential, that has to be 15 joules, and kinetic is 0. And at the bottom, where all we have is kinetic energy, we have to have no gravitational, 15 joules of kinetic, to give us a total energy of 15 joules. Remember that this point is the instant before it hits, right? We don't want the ball touching the ground because that energy isn't conserved any longer. Okay. Last example, we have a child jumping on a trampoline. The first thing I'm going to do is define this location here. This is where the trampoline would be unstretched, so that's our equilibrium position. This is going to be the maximum downward of the trampoline. So this is going to be where I let height equal 0. And of course, the child on the trampoline flies up into the air. This is going to be the maximum height. I want to treat the trampoline as a spring, so I have to consider GPE, EPE, and KE when I do this. Let's start at the bottom. So here is the child at the max stretch of the trampoline. At that position, the child is not moving, so no kinetic. There is elastic potential because the trampoline is stretched, but there is no gravitational potential because we're at the bottom. The trampoline then starts moving upward. When the trampoline starts moving upward, I gain gravitational potential because I'm up above my 0 position. I still have elastic potential because the trampoline is still depressed a little bit, and I'm moving, so I have kinetic as well. At the equilibrium position, I have gravitational potential because I'm up above my 0 position. I do not have elastic potential because I am at the equilibrium position. And I do have kinetic energy, and at this point the kinetic energy will be maximized. If you think about it, the trampoline is moving upward, but as soon as the child leaves the trampoline, it's back to a projectile motion question, and the child's going to start slowing down. We can then look at the child while the child is in the air. The child is no longer in contact with the trampoline, therefore no elastic potential. We do have gravitational potential, and we have kinetic. And finally, the child reaches the max height, which means our gravitational potential is going to be maximized because we will have no elastic potential, again, not in contact with the trampoline, and no kinetic because we're not moving.